Hello everyone, myself Pratna, here to explain you about river flood detection using IoT with Python program and Django framework. So let's look into it. So the agenda of our project is to introduction to flood detection, problem statement, literature review, proposed system, system architecture and hardware components, as well as software components, methodology and implementation, data flow and algorithms, and some of the code snippets and simulation. And at last, we'll look into the results and analysis and conclusion and further work, as well as references. So, introduction. What is flood detection? Flood detection involves monitoring water levels, rainfalls, and environmental factors to identify and to predict flooding events in rivers, urban areas, or lowlands. Traditional methods rely on manual logging stations, which are costly, slow, limited in coverage. Modern approaches use IoT for real time data collection, enabling proactive response to mitigate damage. Importance of flood detection. Why flood detection is required? Because it saves lives by providing early warnings, reduces economic loss such as property damage, agricultural impacts, etc. Supports disaster management in flood prone regions like rivers, basins in India, such as Ganges and Brahmaputra. So let's look into why the role of IoT in flood detection is required. So IoT sensors such as ultrasonic for water level, river gags collect data remotely. Data transmitted via wireless protocols such as MQTT to cloud servers, integration with AIML for prediction and GIS for mapping and flood events. So our project focus combines IoT hardware with Python for data processing and Django for a very user-friendly web interface. Targets river water flood with real-time monitoring, forecasting and alerts. So the main problem statement is current challenges in river flood management. Lack of real-time data, manual systems delay warnings, leading to unprepared evacuations. Inaccurate predictions. So, the traditional model ignores dynamic factors such as rainfall, intensity, and river flow. Urban and agricultural impacts, such as in areas like Bangalore, prone to flash floods, poor drainage, and other issues affecting livelihoods and infrastructure. So, specific problems addressed are limited sensor coverage, sparse networks, mislocalized flooding in river subcatchments, data overload, handling big data for multiple sensors without efficient processing, prediction accuracy, incorporating ML to forecast flood levels based on historic and real time data. So, delayed flood alerts, need for instant notifications via SMS or web to other communities. So, our project goal the design is to design a low cost, secure IoT system for river flood detection using Python for analytics and Django for web based dashboards to achieve a higher than 90% prediction accuracy using ML models such as neuro-fuzzy networks, enabling GIS integrated flood mapping for visual risk assessment. So, the scope of this project is hardware, deploy sensors along rivers. So, the software, Python scripts for data processing, and ML, Django app for monitoring. The limitations of this is focuses on river floods, not coastal. Assume stable internet for data transmission. So let's look into the literature review. Enhancing urban resilience, IoT based smart drainage system, which was published in Springler 2025, focuses on flood management in Mogadishu using IoT sensors for water level and flow, integrated with Python for data processing and Django for a web interface. Demonstrates a real-time alerts and urban flood mitigation. River Cure Portal, WebGIS for flood simulation, a Django based platform for modeling river floods. Uses Python for hydrodynamic simulations and post GRE SQL for data storage, which includes GIS for visualizing flood extents, secured IoT based flood monitoring forecasts, employs IoT with PSOC microcontrollers and sensors for river flood prediction using genetic algorithm based neurofuzzy network. Python, MATLAB for ML optimization emphasizes secure data transmission. So, literature review national scale big data analytics for food impacts uses Django and Python for a pipeline analyzing food risk and infrastructure process. Crowdsourcing data adrenal time warning for national scale simulations. Flood monitoring and early warning signs. IoT perspective reviews IoT techniques for flood detection, including sensor networks and code integration. Highlights Python based analytics for early warnings. Gaps that are identified are limited integration of Django for scalable, user friendly interface in river specific IoT systems. Our contributions are builds on these days by creating a low cost, secure IoT system tailored for river flood with Python, ML, and Django for real time dashboards. So these are the papers that we have taken. So the system is smart drainage. Sensors that are used in there are water level flow, and framework is Django Python, and ML prediction is basic thresholding. GIS integration is partial. Case study focuses on urban floods in Mogadishu. River Cure Portal, hydrometric Django, Django simulation based, and GIS integration is integrated over here. So secure forecasting, pressure rain, Python, Matplat, NeuroFuzzy, and GA, and GIS integration is not required. National Big Data Pipeline Crowd outsourced is the sensor that we use here, and the framework is Django or Python. So the ML prediction is risk analysis, and GIS integration we are doing it. Proposed architecture. The proposed system uses IoT sensors such as ultrasonic water level sensors, rainfall sensors, and flow sensors to continuously monitor river conditions in real time. IoT node collects sensors reading and sends the data to backend server using HTTP post request in JSON format. The Django backend framework receives sensor data through REST APIs and stores it securely in a database. A flood detection algorithm processes incoming data using predefined thresholds on water level, rainfall intensity, and flow speed. So, the proposed system architecture is based on the analysis. The system classifies the river conditions are safe, warning, or danger. Detected flood alerts are generated instantly and stored for historical analysis and future prediction. A web based monitoring dashboard displays real time sensor values, flood status, and alert notification for authorities. The system enables early warnings, improves disaster preparedness, and reduces loss of life and infrastructural damages. So this is a proposed system, the river flood detection with Python and Django. So in IoT sensor, we use ultrasonic sensors, rainfall sensors, flow sensors, and ESP32. We send this request in the form of HTTP post to the Django backend. So Django backend uses SQLite and detects flood alerts, which are then shipped over to monitoring dashboards. IoT sensors collect real-time data. ESP32 sends data to Django backend. Django processes data, detects flood conditions, web dashboards, display live alerts and status. So let's look into the hardware components of the system. So the hardware components are ultrasonic water level sensors, measures the distance between the sensor and the river surface to determine real-time water level changes. So the rainfall sensor detects rainfall intensity and duration, which helps in identifying sudden increase in flood risk. Water flow sensor measures the speed and volume of water in the river to analyze food severity. ESP32 microcontroller unit acts as the main controller to collect sensor data and transmit it to the backend sensor via the internet. Power supply unit provides a stable power to sensor and microcontroller. So the software components that I used in this project are Python, used for sensor data processing and implementing flood detection logic. Django framework manages backend operations, REST APIs, and communication with IoT devices. REST API transfers real-time sensor data from IoT hardware to the sensor servers. Database SQLite or MySQL stores sensor readings, flood status, and timestamp securely. Web dashboards, which are in HTML, displays live flood status and alerts for monitoring authorities. Methodology. Methodology comes in 5 phases. Phase 1 is data collection. Deploy sensors at riverside, sample every 5 minutes. Phase 2, local processing. ESP32 filters noise and computes averages. Phase 3, cloud upload. Use HTTP post to send data to servers. Phase 4, analysis. Check against thresholds, predicts using ML if trends indicate rise. Phase 5, alert generation. Send notification via to load API or email. The flowchart describes the start, read sensor, process, upload, analyze, and alert, and then end. This is the diagrammatic representation of the methodology, which has the start phase, the read sensor phase, where ultrasonic rainfall flow is detected, which goes through process, which has ESP32 file, which filters noise, computes averages and all, uploads use HTTP post method and analyze, check thresholds, and we end the process. So the phase 1 indicates data collection, deploy sensors at riverside, sample every 5 minutes. The local processing ESP32 filters noise and computes averages. The cloud upload uses HTTP post to send data to the server. The analysis phase checks against the thresholds, predict using ML if the trends indicate rise. And the alert generation sends notifications via Twilio API or email. So implementation details. So sensor integration is done through HCSR04 trigger pin to ESP32 using GPIO5 echo to GPIO18. The rain sensor analog pin to AO. Networking Wi-Fi connect SSID pass. HTTP client for API calls. Cloud setup create things peak channel with fields for level, rain, flow, etc. Security use HTTPS and API keys for data transmission. Challenges faced in this implementation is signal interface in remote areas, mitigated with error handling. Data flow and algorithms. Sensors which we use are ultrasonic, rain and flow. Collects real-time real river data. ESP32 reads sensor values and performs basic noise filtering. Process data is formatted as JSON. ESP32 sends data to Django server using HTTP post. Django backend stores data in the database. Flood status is analyzed and alerts are generated. Results are displayed on the web dashboard. Algorithms. The start of the algorithm system initialize sensors and Wi-Fi connections, read water level, rainfall and flow of data, filter noise and compute average values, send data to server via HTTP post. Receive data at Django backend, compare values with predefined thresholds. If values exceed threshold, then flood alert, else normal status. Store data and update dashboard, and this ends the process. These are the code snippets that we have generated. The sensor data model, the Python model, class sensor, def init, self name, location, latitude, longitude, warning level, critical level. Self name is equal to name, self location is equal to location, self latitude is equal to latitude, self longitude is equal to longitude. This purpose of this code snippet is to represent a flood monitoring sensor with threshold levels using Python. Code snippet number 2, reading water level data. So we import random def read water level simulated sensor reading in meters written round random uniform 0.5 to 9.0, comma 2. Flood level classification logic. So diff classify level current level warning is critical. If current level is greater than or equal to critical, written critical. Else if current level is greater than or is equal to warning, written warning. Else written normal. The fourth code snippet is alert triggering system. So diff generate alert sensor name status. If status is critical, critical alert at sensor name. If status is warning, then return warning at sensor name. Return all conditions are normal. This generates alerts for authorities and users. Sensor monitoring loop. Diff monitor sensor level is equal to read water level. Status is equal to classify level, level sensor warning level. So this purpose of this sensor monitoring loop is to core logic that monitors system sensors continuously. So these are the output screenshots of the project that have been built to provide an overall view about the range of river water level. So the results and analysis phase include simulation results where the accuracy is 92% in detecting threshold breaches. Response time is 1.0 seconds, which should be greater than or is equal to 10 seconds for alerts. And power consumption is 200 mega ampere during transmission. Graphs use line chart and bar chart. Water level versus time. Peaks indicate flood risk. Bar chart indicates rainfall intensity and comparison. Evaluation metrics includes precision recall for ML model tested on 1000 data points. Limitation of this model is dependent on internet. Battery life is extreme in extreme weather. So these are the results and analysis of river flood detection system, where the simulation is the proposed system was tested using simulated and real-time sensor data. The flow detection accuracy achieved was 92% and the power consumption is 200 megaampere during the transmission. Graphical analysis. The line chart indicates water level and time, shows gradual and sudden rises in water level. Bar chart includes rainfall intensity comparison. Evaluation metrics include evaluated using 100 data points. Precision includes high precision indicates most detected flood alerts were correct. Recall indicates high recall confirms the system successfully detected more flood events. Limitations. The dependent on internet connectivity in remote areas, battery life may reduce under continuous operations and extreme weather conditions. These are the graphical analysis where a line chart is shown with the water level and the time. Shows a gradual and sudden rise in water level. Sharp peaks cleanly indicates potential flood scan conditions. So this is the line chart, this is the bar chart, and this is the overall analysis of it. The system demonstrates fast, accurate, and reliable flood detection using IoT sensors and Django based analysis. The system demonstrates fast, accurate, and reliable flood detection using IoT sensors and Django. So the conclusion of this is an IoT based river flood detection was designed using ESP32, Python, and Django for real time monitoring. The system continuously collects water level, rainfall, and flow data and transmits it securely to the backend server. Flood conditions are analyzed using threshold basic logic, enabling early detection and alert generation. The system is cost efficient, scalable, and suitable for real world flood management, despite minor limitations like internet dependency. These are the references from which we have referenced for building this project. Now let's look into the demo of our project. So our HydroGuard AI helps in detecting all the sensors and all the datas, the flood levels and all the critical warning signals that a sensor provides. So let's look into the North Bridge Station, which is present in the Upper River District. Here we can look at the status, the condition, which is normal as of now, and this is the exact pinpoint location, the latitude as well as the longitude of this location. The current level is 2.50 meter, which is absolutely normal. The warning threshold is at 5 meters, which is if this level increases to 5, then warning threshold is provided to the host system so that critical actions can be taken. So the critical threshold is 8 meters and the max recorded of this particular place is of 5.50 meter and the average level usually is 3.82 meters. So this is the historical water length of it, and we can see that it was quite low before, and during the time of 912, we can see that the water level has increased to 5.50 meters, which has sent a warning signal to the host device. This has happened on February 8th, and these are the recent reading stamps that we can look into. And here we can add another sensor as well by providing the sensor name, the location description, and the latitude, longitude, and we can also tweak the warning height meters and critical height meters here. Thank you.